Thumbs up if this is visible. Thanks very much. Hi, my name is Peter Sullivan. I'm here with Mio Lee, and we're here to talk about speech technology for everyone, automatic speech recognition for non-native English with transfer learning. I'd like to thank my colleagues Toshiko Shibano, Xin-Yi Zhang, Heijin Cho, and Mohammed Abdul Magid. Our work evaluates fine-tuning strategies for adapting large pre-trained L1 English ASR models to L2 English speech. By L1 English, we mean, of course, native English speakers, and L2 English is non-native speakers.
Thanks, Peter. Now let's start with why we care about English spoken by non-native speakers at all. The short answer is there's a lot of them, or a lot of us, I should say. As of 2003, the L2 English speaking population was 3 times that of L1. And this ratio has probably gone up in the last decade because the population growth in areas where English is a second language is about 2.5 times that in areas where it is the first language. And with the size of a population group like this, potentially providing lots of data, we would think that the ASR technology for L2 speakers would already be quite developed. Yet we still see a significant performance gap on L1 and L2 speeches. Next slide, please. And this performance gap is mainly caused by 2 factors. One, the influence of a speaker's native tongue to their later learned language, and 2, data scarcity. So the first point is referring to the pronunciation of words that L2 speakers are likely to carry pronunciation habits from their L1 language when they're speaking English. And on the left of the slide, we have some examples of errors that the ASR system made on L2 speeches. Now moving on to the second point, data scarcity. It is commonly acknowledged that there is a lack of publicly available, annotated, and high quality L2 speech data. Although there are some speech corpora out there constructed for L2 English, the amount of data is not nearly comparable to that for native English and not nearly enough for training models from scratch.
So our starting point is using the state-of-the-art pre-trained ASR model, Wave2Vec 2.0, specifically the model trained on 960 hours of LibreSpeech with self-training on 60,000 hours of LibreLite. This is a high-performance model that performs well even without language model decoding. For our fine-tuning data, we use the L2 Arctic dataset. This is a 27-hour dataset based on CMU Arctic, which is the L1 English dataset. L2 Arctic has good phonological coverage, and covers 6 native speaking languages with 2 female and 2 male speakers for each accent. We evaluate several different training strategies. Does training on pools of different backgrounds of accent improve performance, or is training on a single accent more beneficial? Because we're working with a small number of speakers in this data set, it's important to identify how much of a gap there is between speaker-dependent and speaker-independent models. So we also simulate situations where we have unknown speakers and test on their performance. Finally, we look at pairs of different accents to see if 2 different accents may benefit from pre-training. This is a brief overview of our experiments. So we've looked first at a single accent training versus a multi-accent training. Then we look at speaker-dependent versus speaker-independent effects. And finally, we look at pairs of accent trainings.
Yeah, so the first training scenario is the training of single accent and multi-accent models. The single accent models, given by their names, are models trained and evaluated on only 1 accent per model. As Peter mentioned earlier, the L2 Arctic corpus includes 6 L1 accents, which naturally divides into 6 subsets of data for the 6 single accent models. Within each subset containing only one L1 accent, data were further split into the train, dev, and test sets, with no utterance overlap across them. And the multi-accent model was trained and evaluated on all data from L2 Arctic, meaning that all 6 L1 accents appeared in the train, dev, and the test sets. But of course, no utterance overlap across the 3 sets either. The purpose of this set of experiments is basically to see when should we go for a single accent model in our real life use cases, and when should we go for the multi-accent one. And here we give you some takeaways based on our results. Next slide, please. So the first takeaway is that if you know which L2 English accent you're working with and there's data available, then train a single accent model. From our results, if you look at the comparison highlighted in red, where model 1 is the multi-accent model, all 6 single accent models outperformed the multi-accent model on L2 Arctic. And not only that, most of them also exhibited minimal performance trade-off on native English, and that's shown in the blue shaded regions. The second takeaway is that the multi-accent model is a well-rounded, generalized model. It's true that it's not as high-performing as the single accent models on a particular accent, but it still improved the performance compared to the baseline on all accents. This means that if you're not sure which L2 English accents you'll bump into in deployment, training a multi-accent model would help.
With large corpora, you can set aside speakers for a test set and report speaker-independent results. But because we have so few speakers in our data set, we aim to quantify the gap between speaker-dependent models, which is to say models that have seen speakers in both train and test, versus performance on unseen speakers. We use a cross-validation approach. One speaker of each accent is held aside and the rest is trained on. We repeat this for each fold, ensuring gendered balance mini test sets, and repeat a similar process with the single accent examples, where we take out one speaker for each of the splits. We find about a 10% worse word error rate for our multi-accent independent model compared to the model 1, which was a speaker dependent model. And came in at around 9.27 word error rate. For our single accent models, we compare performance on all speakers in the accent, which is this test all column, with performance on just the left out speakers, which is the test 0 shots speaker column. We notice roughly a 10% worse performance for some of the accents, Spanish, Korean, and Hindi, and up to 18% on Arabic. This sets a general limit on performance downgrade between using a speaker-independent model and a speaker-dependent model.
All right, and the last training scenario is about the accent transfer effect under the 0-shot setting. That is, what if there's no data available for the accents we're trying to recognize? And again, we consider cases with single accent models and with multi-accent models. First, let's talk about the single accent models. In this set of experiments, we took a single accent model, which again was solely trained on one of the 6 accents. And since this is the 0-shot setting, we evaluated it on all other 5 accents except for the one it's trained on. And we did this to all of the 6 single accent models. Now as for the multi-accent models, we trained a model on a train set comprising 5 of the 6 accents and evaluated it on the other accents left. And we repeat the steps and we got 6 multi-accent 0-shot models for the 6 accents. Next slide, please. So this table shows the performance of the single accent models on all accents. The takeaway here is that some accents are mutually beneficial. meaning that the knowledge a single accent model obtains from accent A can be applied to accent B. For example, the blue highlighted areas show that the model trained on the Chinese accent also improved performances on the Vietnamese and the Korean accents. And the reverse is also true. So the Chinese accent also benefited from models trained on the Vietnamese and Korean accents, respectively. However, this is not always the case. So the Hindi accent, shown in red, for example, did not improve recognition on any accents other than itself, nor did it benefit from other accents. So you'll see that there are similarities and differences in pronunciation variations across different accent groups, and these might determine whether two accents can be mutually beneficial in terms of accent transfer. Next slide, please. And finally, the multi-accent models. They are a sorry, someone's mic is on. Can we just all mute, please? I'm gonna continue here. Finally, the multi-accent models. They're a more general solution to the zero-shot problem. So the table here shows that the multi-accent models were still able to beat the baselines on all 6 accents under a zero-shot setting. And even for the Hindi accents, so the one that did not benefit the other accents nor benefited from the others, we still see that the multi-accent model was able to leverage knowledge from other accents and improve the performance on Hindi under a zero-shot setting.
So in summary, we found that fine-tuning Wave2Vec 2.0 with small amounts of labeled data does indeed improve L2 performance. We were able to quantify the performance gap between speaker-independent and speaker-dependent models. We also identified that some pre-training is beneficial for specific pairs. So for instance, for Chinese and Korean, both benefited from pre-training on the opposite language. But for some languages, this was not the case. Finally, in our most optimistic scenario, when you know the target audience of your tool, single accent models boost the performance the most. However, multi-accent models and zero-shot models also perform fairly well. Thanks very much.